I guess it's fine now. Yes, I go ahead now. Thank you for your patience, audience. There is some technical issue. Yes, it is resolved now. Yes, with continuation of this chapter, the term magnetic effect of electric current means that an electric current flowing in a wire produces a magnetic field around it. What we have learned last class. We have taken a wire and connected to battery terminals. Now current is flowing through the wire. Nearby, we placed a magnetic compass needle. Then this magnetic compass needle is started fluctuating. Okay. Now we see that needle is deflected. What does it mean? Yesterday we saw that it means that the electric current through the copper wire has produced a magnetic field. Thus, we said that electricity and magnetism are linked to each other. Okay. Now, then what about the reverse possibility of electric current of moving magnets? That we discussed. And this experiment also we did it. We taken a bar magnet and we taken a magnetic compass needle. Magnetic compass needle, magnetic field lines we chose. So why does a compass needle gets deflected when brought a magnet? So we placed iron filings and bar magnet. After placing, yes, all the iron filings are attracted only at the poles. Now, the space surrounding a magnet in which magnetic force is exerted is called magnetic field. The path traced by a north magnetic pole free to move under the influence of magnetic field is called magnetic field lines. So yesterday we have discussed current carrying conductor will gives a magnetic field. Then there are few questions we have solved, and current carrying conductor straight line. So identification Maxwell right hand thumb rule. Yes. Now current carrying conductor in a circular loop. If you give a current through one part of the wire, a current is flowing entire the circular coil. So again here we used Maxwell right hand thumb rule. According to Maxwell right hand thumb rule, we noticed that one end, let's say current upward direction, another end which is downward direction. So again once the current direction changes, magnetic field directions are changed. as we away and away from the center, the concentric circles represents a magnetic field becomes bigger. Now at the center of a circular loop, the magnetic field lines are straight. By applying right hand thumb rule, it can be seen that the segment of yes please yes Susan, you can ask me a question. Very interesting question. Yes, my topic is magnetic field, but yes, I'm respecting this question. The student is asking a question that as light from a star spreads out and weakens. Do gaps from the between the photons? Okay, here the concept is yes. Generally, the light, the star is not a natural source of light. It's not a natural source. Some stars are the natural sources, but not all. But as you asked, the light rays coming from the stars, however, while coming from the millions of kilometers, there is a refraction, the process of refraction. The star is blinking from down to top whenever we are seeing. The light rays are traveling from different mediums of atmospheric regions. So finally the different ways it bends. That's the reason star looks like a twinkling. Now there is a question again. In that question, the star spreads out. The light from the stars spreads out. Yes, this is diffraction. Due to the diffraction, yes, it spreads out because medium is changing continuously from star to earth and weakens. Of course, when the light ray travels of millions of kilometers, yes, it weakens because light photons get discharges. Automatically it will be dissolves the energy. We can't receive the actual light what we are getting from the star. Yes, photons energy is decreasing due to more distance. I hope it solved your doubt. One is due to a distance more, the energy of a light photon will be decreased. We can't run as much as long distances. We have certain energy. If energy dissolves, yes, we can't regain back while the movement. Yes, I guess this answer has helped you. Shall I proceed? Wow, fantastic question. One more question. Can momentum be hidden to human eyes? Like how kinetic energy can be hidden as heat? Uh, Here nothing is the hidden part. In fact, nothing is hidden. We can call it as an enthalpy. Enthalpy is a concept over here. It is a storage of energy. The momentum can be hidden to human eyes. It's not a part of hidden over here. The human eye, for example, if any object which is in the movement, the mass and velocity we can call it as momentum, product of mass and velocity. So due to the special theory of relativity, the momentum can be changed. It's not hidden part of thing, it's a change. As a special theory of relativity of mass and velocity, m dash is equal to m by square root of 1 minus v square by c square. It depends on the light velocity. Light velocity is of course constant, depends on the object velocity. Once object velocity changes, yes, of course, momentum also change. That we can call it as an enthalpy kind of thing. Because how kinetic energy can be hidden to the heat, yes, it's a part of enthalpy. Thank you so much, dear friends, audience, students and teachers. Yes, you can feel free to ask a question at any point of time. I'm honored to answer your questions. Yes, I'll continue my chapter. Current carrying conductor in a loop line. Here, initially we have taken a straight line. Current is flowing from one direction. So we applied Maxwell right hand thumb rule. Thumb finger along to the current direction. Remaining four fingers we folded. We identified magnetic field direction. Now the same length of a wire, we made it in a loop line as per the diagram. Now both the ends you connected to battery terminals. Now current is flowing from left hand side to right hand side. So let's say left hand side current is upward direction, right hand side current is downward direction. Now apply Maxwell right hand thumb rule left hand side. So always thumb finger will be the thumb finger will be the current direction. Remaining four fold fingers will be magnetic field direction, which comes as anti-clockwise. While coming another end, yes, thumb finger which is downward direction. Remaining four fold fingers will be clockwise direction. So what you understood? Once current direction changes, magnetic field direction is changing. Fine. Now the distance between two wires increases, magnetic field of the center will be decrease, because from the center of the wire to the distance increases, the magnetic field strength will be decrease. As a simple experiment I'll tell you. Take a candle, lit a light, okay, put a finger far away. We can't observe that much heat energy. Put a finger slowly near to the flame. Yes, we are getting heat energy. Similar way, magnetic field which is very near to the wire, once if it is increases the distance, obviously magnetic field will be decrease. Next. Yes, there is a question. In CBSE, they'll ask this question. They'll ask you what kind of magnetic field it is, where we noticed. Is a straight line current carrying conductor, or a circular coil, or a solenoid, or a short straight wire. This kind of diagram will come in circular coil. This is the most important repeated question. Now coming to solenoid. What is solenoid? We will explain in a easiest way. Take a wire, turn into n number of loop lines, Before only single loop, only one loop, but we made it as a circle with the same radius. So this we can call it as solenoid. In easiest way, inside of the pen there is a spring will be there. Exactly the spring itself is solenoid. How that spring looks like, solenoid also look like the same. Now, how to define a solenoid? A coil of many circular turns, insulated copper wire wrapped closely in a shape of cylinder is called as a solenoid. For example, you forgot this definition in examination time. So how to recollect it? How to remember it at the point of examination? You know that the spring how it is. The spring look like number of circular loops with the same radius. Okay, just give a moment. Yeah, the solenoid we can define as number of loop lines or number of circular loops. Here I am mentioning the number of circular loops with same radius. As a one sentence is sufficient. Number of circular loops with same radius. If you not write same radius, teacher may understand in a different way. Number of circular loop lines. This is also number of circular loop lines only, but this is not a solenoid. With the same radius, exactly this is a solenoid. Fine. The students can able to simplify the definition. Now, how that magnetic field will be, we will see that. Take a number of loop lines. Here I am mentioning. We connected both the ends of the wire to the battery terminals. Okay. Number of circular loop lines with the same radius, we can call it a solenoid. Both the ends we connected to battery terminals. Now one is positive, other one is negative. Now current is moving from one direction to another direction. You can observe the current direction is keep on changing. the current direction is keep on changing. Yes, you can see the down all one direction, the top line all one direction, alternative of the wires up and downs we noticed. So now as you know that current carrying conductor is giving a magnetic field. How to identify the magnetic field now? Can we apply the right hand thumb rule? If you apply the right hand thumb rule, each and every point we need to turn, which is very difficulty. Each and every time the four-fold fingers we need to fold it. It is a mesh up. Magnetic fields we can't identify. So which formula which is applicable? And which theory is applicable to identify the magnetic field lines? Yes, very good evening, Shish. If any doubt is there, feel free to ask me regarding magnetic fields or any other part of physics. So each and every direction current is changing, we can't apply the four-fold fingers in easiest way. But how to identify the magnetic field lines? Now generally teachers will say that the top line will be this is the way, the down line will be so and the center one so and so like this. But how to prove that? And which one is the north pole, which one is the south pole? This is the most important over here. Now after giving a battery connection, then automatically current will be flow through the wire. Yes. So we can't identify the magnetic field lines while using Maxwell right hand thumb rule. But how to identify the magnetic field lines is a major question. For that we need to use clock face rule. What is clock face rule? As simple. Let's say letter N. Letter N. N is end part, you can see the end part which is rotating like this anti-clockwise. Yes. If current direction is anti-clockwise, that pole is north pole. If current direction is clockwise, that pole is south pole. So one end part which is rotating down, that end part anti-clockwise. Wherever the current direction is anti-clockwise, that side is north pole, and clockwise direction, that is south pole. So now, yeah, clockwise direction. Yeah. Yes, Ashish, I can say this. Any three appliances that can function Fleming left-hand rule. Yes, upcoming subchapter is Fleming left-hand rule. Just wait for a few minutes. Of course, we are going for Fleming left-hand rule. Appliances will be discussed. Yes, all 5 questions I'll explain you. Now, in a upcoming solenoid, current direction is anti-clockwise. So this is the way. We connected the battery and current is flowing anti-clockwise. So this part is clockwise. This part is clockwise. This is south pole. Opposite pole is north pole. Okay. Let's say current is not flowing. This is the direction. Current is flowing this direction. So now anti-clockwise. Anti-clockwise again the north pole. Top of the spring and the down of the spring, magnetic field lines are very closely loop lines. Like this. At the same time, down also. All students remember, always magnetic field lines from north pole to south pole. Yes, north pole to south pole. Top also, down also, mandatory we need to show the arrow marks. In CBSE board examination, arrow marks are the most important. Now, through the axial, magnetic field lines are south to north. South to north. Probably now, the solenoid magnetic field lines, bar magnet magnetic field lines are the same. Clear? Yes. Next, there is a questions for you. What you have understood from this subtopic, I'm asking question to all the audience. The magnetic field inside a long straight solenoid carrying current is 0, decreases as we move towards its ends, increases as we move towards its ends, is the same at all points. A repeating question. Magnetic field inside a long solenoid carrying current, inside, not top down, inside. Is inside will be 0? No. Decreases as move towards its ends? No. Again, more power is there. Increases as move towards its ends? Increases as move towards its ends? Is the same at all points? Of course, the center line will be the lines we showed that. The right answer is same for all the points. It won't be increase, it won't be decrease. Next, the direction of the current in the coil at the end of the electromagnet is clockwise. The end of the electromagnetic will be south pole. Clockwise, south pole. The magnetic field lines in the middle of a current carrying solenoid are parallel to the axis of the tube. Yes. One student asked me the question, what is appliances of Fleming left hand rule? Fleming left hand rule, generally the force it will be. Yes, the force of a current carrying conductor we are identifying through Fleming's left hand rule. Okay, let's say when that the force will be create electrical energy to mechanical energy. Once mechanical energy creates, that is, the first one is electric motor. Okay, electric motor force can be created. 3 appliances. The student is asking 3 appliances. Electrical energy to mechanical energy, only motor, what I know. But remaining 2, yes, I'll come back to you, student Ashish, audience Ashish. Remaining 2, I'll let you know that. And any other questions? Any other questions? We'll see. Yeah. We'll continue until the questions. Now, what is Fleming left hand rule and how it works? We will see that how that force will be created. Take an iron rod and freely suspend it to retard stand. Now give the power connections to both the ends. Okay. Now current is flowing from one end to another end. Once current flows, magnetic field will be created. So we applied extra horseshoe magnet. What happens? Force will be created. So how to identify the force? For that, Fleming left hand rule. One student asked the question, the left hand rule related question. So the center finger will indicate current direction, index finger will indicate magnetic field direction, the thumb finger will indicate force direction. Okay, and center finger, index finger, thumb finger mutually perpendicular. Mutually perpendicular. So we need to place the thumb finger along to the current direction, index finger to the magnetic field direction, thumb finger to the force direction. So this is the way we can able to calculate the force. Yes. Why does the rod gets displaced? Why that force is creating? The magnet exerts a mechanical force on current carrying wire, is free to move the force and can produce a motion in the wire. The direction of force acting on the current carrying wire in a magnetic field is perpendicular to the direction of current and the direction of magnetic field. The maximum force is exerted when current carrying wire is perpendicular to the direction of magnetic field. Yeah. So this is Fleming left hand rule. All right. Yeah. According to this rule, stretch the thumb, forefinger and middle finger and the left hand such that they are mutually perpendicular. If the first finger points the direction of magnetic field and the second finger in the direction of current, and the thumb finger will point in the direction of motion of the force acting on the conductor. Yes, there are few questions related to the force, and this we can see from tomorrow. Very important questions we'll discuss in tomorrow class. Thank you so much for attending of the session. And daily Monday to Saturday night 10 to 11 p.m. live stream classes for the rural India. Thank you. Jai Hind.